Okay, so in this section, we want to discuss what are called planar graphs. So here's a definition of a planar graph. A graph G is said to be planar if G can be drawn in the plane, this is why it's called planar, in such a way where no edges cross each other. So in essence, I want to be able to draw my graph G in such a way that no two edges cross each other. If I can draw it in such a way, then the graph is said to be planar. So let's take a look at a couple of examples. Okay, K4 is planar. So let's recall. What was K4? The complete graph on 4 vertices. So 1, 2, 3, 4. And if we remember, there was a way to get from each vertice to any other vertice. So this is K4, okay? Now, you might be saying, well, wait, Professor Wicks, you drew it and the edges are crossing. Yes, you are correct. Notice that these edges right here are crossing each other, okay? But my claim is this, is that this graph can be redrawn as follows. I can redraw this graph. Let's say I have V1, V2, and V3. What's the definition of K4? I've got 4 vertices, and I need to draw it in such a way that no two edges overlap. So V1 is going to connect to V2 and V3. V2 is going to connect to V1 and V3. Okay. I guess I'll shade the edges that I've done right here. So V1 is connecting to V2. I've got him. V2 is connecting to V3. I've drawn him right here. V3 is connected to V1. That's this edge right here. Now, I need to draw, or I need to add in a vertex, V4, and connect it to all the other vertices, V1 and V2, in such a way that no edges are going to overlap. Well, what if I put V4 right here in the middle and connect V4 to V1? That's this right here. V4 to V2, that's this edge right here. And V4 to V3, that's this edge right here. I'll redraw it better over here. Like so. Now my claim is that this is the graph K4. But notice I've drawn it in such a way that no edges cross each other. In essence, I have drawn this in the plane in such a way where no edges cross each other. So we say this is a planar graph. Let's take a look at another example. K23 is planar. Okay, so let's recall what K23 looked like. Recall, K23. This was the complete bipartite graph. So I have 2 vertices in my first set and 3 in the second set. Like so. And I might label these V1, V2, and then these other ones U1, U2, and U3. So my claim is that this guy can be redrawn as follows. Well, let's take a look. Okay? Let's take a look at V1. Who is V1 connected to? V1 is connected to who? U1, U2, and U3. Okay, so let's draw it as follows. Let's go to U1, U2, and U3. Okay. Well, who is U1 connected to? U1 is connected to V1 and V2. So let's connect him over here to V2. Well, who is V2 connected to? V2 is connected to U1, U2, and U3. So let's connect V2 to U1, U2, and U3. And my claim is this is the graph of K23. Notice V1 is connected to only U's. Here they are. U1, U2, U3. V2 is connected to only U's. U1, U2, U3. U1 is connected to only V's. V1, V2. U2 is connected to only V's. V1 and V2. And U3 is connected to only V's. V1 and V2. And so my claim is that K23 can be rewritten or redrawn as follows. And now notice no two edges cross each other or overlap. And so we would say K23 is planar. Now, when a planar graph is drawn without edges crossing, the edges and vertices of the graph divide the plane into regions, and we call each region a face. So let's take a look at K23. When I draw it in the plane as follows, notice I get face 1, face 2, and then outside is face 3. And so I have these segments right here are called the faces, and then everything else outside of it is face 3. Each region is called the face. What about K4? We looked at him just a second ago. What did he look like? When I draw him in the plane, he looks like this. Like so. What are the regions? I'll just label it 1, 2, 3, and then outside 4. So each region, I call it a face. Okay. Let's now discuss Euler's formula for planar graphs. Euler's formula for planar graphs. Let G, V, E, F be a connected planar graph with V vertices, E edges, and F faces. Then V minus E plus F equals 2. And so we call this Euler's formula for planar graphs. So let's verify Euler's formula for K4. So what did K4 look like? I feel like I've drawn it 3 times because I have. Like so. Okay. So, how many vertices in the vertex set? This was V1, V2, V3, V4. How many edges E in the edge set? That's 1, 2, 3, 4, 5, 6. 6 edges in the edge set. And how many faces F? Well, let's look. This was face 1, face 2, face 3, and remember, there's a 4th one out here, face 4. So, this graph is planar. Because this graph is planar, V minus E plus F equals 2. So 4 minus 6 plus 4, is that 2? Well, let's check. 4 and 4 is 8, minus 6 is 2. It checks out. So we just verified that this was true. Okay. What if I did it for K2, 3? This one that we just did. So K2, 3. Like so, redrawn as follows. How did we do it? We did it like this, here, 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 here. Okay, so let's ask this question. How many vertices in the vertex set? That's 1, 2, 3, 4, 5. So V equals 5. How many edges in the edge set? That's 1, 2, 3, 4, 5, and 6. And how many faces? Face 1, face 2, and outside face 3. So 3 faces in the edge sets. Excuse me, in the 3 faces in the face set. So V minus E plus 5, does this equal 2. Well, 5 minus 6 plus 3, is that 2? Well, let's check. 5 minus 6 plus 3. 5 plus 3 is 8. 8 minus 6 is 2. 2 equals 2. Sure enough, it worked out. Okay? So this Euler's formula, it's important. Okay? The graph must be a planar graph. If it is planar, then this formula works. Okay, let's do this last example right here. Theorem. The graph K5 is non-planar. Okay. Slide over here and do this one in PowerPoint. Okay. The graph K5 is non-planar. Okay? So let's do the proof. And we're going to do it by contradiction. So, how do we do proof by contradiction? We suppose the contrary. We first suppose K5 is planar. Now we're going to show, hopefully, that this is going to lead to an absurdity and it's going to be a contradiction. So suppose K5 is planar. Remember, K5 looks like this. It's got this star inside of my pentagon. Okay, so suppose K5 is planar. That is, K5 can be drawn without edges crossing. Okay, well, for K5, the number of vertices is 5, and the number of edges is 10. Using Euler's formula for planar graphs, and I can do this because I am supposing or I'm assuming that K5 is planar. So using Euler's formula for Planar's graphs, okay, what was the formula? It was V minus E plus F equals 2. So 5 minus 10 plus F would equal 2. Would imply then that F would have to equal 7. Notice 5 plus 7 would be 12. 12 minus 10 would be 2. Okay? Now, using the handshaking theorem, the sum of the degrees for all faces must satisfy 2e bigger than or equal to 3f. which implies 2 times 10 has got to be bigger than or equal to 3 times, what do we say f was? 7. So 20 has got to be bigger than or equal to 21. Well, this is false. A contradiction. So we conclude our assumption that K5 is planar is therefore false. Hence, K5 is non-planar. What does that mean? That means I cannot draw this graph, K5, in such a way that no two edges cross each other. So this graph, K5, is non-planar. And there we have it. Similarly, K33 is non-planar. What do I mean by K33? This would be this graph as follows, the complete bipartite graph. This graph right here, K33, is also non-planar. If I wanted to prove it, I would do a very similar proof to proving K5 is non-planar. So that's going to conclude our discussion on planar graphs.